Hi, this is the October 2021 edition of PAC's monthly webinar series. If you want more information about PAC International, our products, and the webinar series, you can go to pacinternationalllc.com. There you can find, amongst other things, registrations for upcoming webinars and also video recordings of past webinars. Today's topic is acoustic ratings, the STC, IIC ratings that have been around for many, many years. And we're also going to talk about two new ratings, the HIIC and LIIC. We'll start with a quick overview of our topics for today. So first, we're going to talk about the STC and IIC ratings and what are they. Then we'll talk about the difference between lab and field measurements. There are some important points there to keep in mind. We'll talk about myths and misconceptions. I'm certainly not going to cover all of the ones related to STC and IIC ratings, but I'll talk about some of the ones that I get commonly asked about, that I see commonly, and try to address those. Then I'm going to go in a little bit deeper into this, and I'm going to talk about reading STC and IIC graphs. Acousticians, these are something that we look at a lot because they give us a lot more detail, a lot more information that we can use for our designs, information beyond the STC and IIC single number ratings. And so we'll talk about that. So if you see those in a test report or something, hopefully you'll have a better understanding of what they are, what they represent. Then we'll go on further and we'll talk about how STC and IIC ratings are calculated. Then we're going to get into some of the shortcomings of the STC and IIC ratings, some things to look out for. We'll talk about that in some detail. And that will lead us into these new ratings, the HIIC and LIC. And finally, we'll talk about methods of improvement, right? Ways to get better STC, IIC, and also HIIC and LIIC ratings. Because ultimately, PAC International, we produce acoustical products, and that's what our goal is to help improve these ratings. So before we get into all of this and we start talking about the ratings and things like that, right, there are code minimums for STC and IIC. Those code minimums are STC and IIC 50. Many of you listening to this are probably familiar with those, right? But I want to start out with this quote. So with the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to a reduced quality of life and possibly to negative health effects. And a webinar down the road, I'm going to dig into a little bit more of the health effects of noise. It really is a big issue. It's a public health issue. Noise is a significant environmental pollutant. I'm not going to get into all of that today, but just keep in mind that there really are significant health effects for noise. Noise causes stress, and stress has all of these knock-on health effects, right? And this quote isn't just from some acoustician saying, oh, we need to do better. This isn't just me trying to sell product or something. This is actually from the International Code Council itself in their 2010 guidelines for acoustics. And there's some great information in there. I would encourage all of you, if you're not familiar with that, to go give it a read. It's not a huge document or anything, and there's some good information. So STC and IIC, what is the difference between the two ratings? What do they mean? How do we get them? So here I have this sort of just cartoon depiction of sort of theoretical test lab. Typically in a test lab, we're not testing walls and floor ceilings in the same space like this shows, but again, just a cartoon for discussion purposes. So start with STC. It stands for Sound Transmission Class. And STC measures the reduction of airborne sound. So when we're differentiating between these tests and the types of sound, we're considering where the sound starts. So ultimately, all the sound goes through the structure that we're trying to test or evaluate, but we differentiate between the types of sound and the types of tests that we do by where the sound starts. So for airborne sound, it's sound that starts in the air, like me talking, right? Right now, I'm talking, my vocal cords are vibrating, that's creating pressure fluctuations, and that goes out, travels through the room where I am. And we'll talk about impact sound differently. So the STC rating applies to walls and floor ceiling assemblies. And some noise source examples would be people talking, and that's really what the STC rating was originally developed around. It could also be TVs, stereos, home theater systems, my kids running around the house yelling at each other, all of these kinds of things, right? The way the STC rating is measured, so we take a noise source, like this speaker up here. We make a bunch of noise in the room, in what we call the source room, and we measure how loud it is in there. And then we go to the receive space, which could be the room below or the room to the side if we're testing a wall, and we measure how loud it is in there. And basically we take the difference, that gives us the transmission loss, and then we use that to calculate our STC rating. So really the STC rating represents how much noise reduction we get from the source room to the receive room. The IIC stands for Impact Insulation Class, and it is a measure of the reduction of structure-borne sound. So again, I said that we're differentiating based on where the sound originates. So for structure-borne sound, it originates with an interaction with the structure. So footsteps, dropped objects, things like that, that are hitting the structure, and that's creating the sound. It applies to floor ceiling assemblies. We don't test IIC ratings for walls. Some noise source examples, right? I already talked about footsteps, dragged chairs, dropped objects, vacuum cleaners rolling across the floor, all of these kinds of things. The way we measure it is we use this thing in the upper picture beneath the word source. It's a tapping machine, and this is a standardized acoustical testing instrument. And inside of it are 5 little weights. They're about 1 pound, and they're usually on a cam, or sometimes there's electromagnets that can lift them up. But they're lifted up so that then they free fall and hit the floor. And in succession, close succession. So you just get this tapping sound on the floor. And so you do that, you put it in specific positions on the floor that are all dictated by the test standard. And then you go and you measure how loud it is in the room down below. And you use those measurements to calculate your IIC rating. And the tapping machine, again, this test is really sort of built around footsteps, footfall, those kinds of things. So it's designed to sort of help if somebody's walking around upstairs. It doesn't necessarily help for big heavyweight impacts from a gym or something. And those are things that we'll get into when we talk about some of the shortcomings and the issues with the IIC rating. All right, so now lab versus field. So in the lab, first we'll just talk about what the ratings are that come out of a lab. So for airborne sound, we have STC, the sound transmission class, right? And for impact sound, we have the IIC, the impact insulation class. And in the laboratory, we work really hard to control flanking paths. Those are ways for the sound to get around the partition that we're testing. So really what we're testing is just those direct paths shown by the teal arrows here. And that's why in this sort of for the lab, I've shown these squares as separate boxes that aren't connected to each other, because in the lab, we try and disconnect the different test rooms that we're using. So the results that we get from the lab only measure the sound that is directly going through the assembly that we're testing. And therefore, the results indicate the performance of that assembly independent of the surrounding structure. In the field test, it's a little bit different. So for the field, we have a number of different ratings. So for airborne sound, we have ASTC, NNIC, and NIC. They're all basically measures of the same thing. How much do we reduce the noise when we go from the source room to the receive room? But there are some nuances in the differences of them and when you can report one versus the others, depending on room dimensions, room absorption, all of these other factors that we don't really need to go into for the purposes of this presentation. Impact sound, again, we have 3 different metrics. We have the AIIC, the NISR, and the ISR. And again, they're all basically measuring the same thing. We bang on the floor upstairs, we measure how loud it is downstairs, and we do a little calculation to get the rating. But again, there's some different parameters with room sizes and things like that that affect which rating you can report. In the lab, again, we've separated all these spaces so that we don't include the flanking sound. But in the real world, all of these things are connected, right? All of these rooms are connected, otherwise the building would just fall down. So we're measuring the sound through all of these paths, not just the direct paths shown by the arrows here. So we might get flanking sound that goes down the walls and then out through the walls in the receiving space, or down the walls and up from the floor. I mean, I did a measurement in an apartment building. It was all concrete construction, and there was a gym, you know, their fitness amenity space, and there was an apartments or a number of apartments below it. And there was a fairly substantial fitness floor that provided quite a bit of impact isolation there. But even then, dropping a 35-pound kettlebell or dumbbell on the floor and going downstairs to the space, not only could I hear the sound, but I could actually feel it in my feet. And I was on the floor below where the impact was. So there was significant flanking, significant transmission of that sound and that vibration through the structure and into the concrete slab that I was standing on. What that means is when we do a field test, the results indicate the performance of the assembly and the surrounding structure. So it includes all of those flanking paths. And that means that then the results are only applicable to the tested assembly and the place where you've tested it, that building and that location within the building, because that has these specific flanking paths. And if you go somewhere else in that building, you may have different flanking paths that give you different results. All right, now that we've kind of talked about what the STC and the IIC ratings are, how we've measured them, let's talk about some myths and misconceptions. The first one is that you can add STC ratings. It would be great if we could. It would make my life a lot easier, much simpler calculations. Less time playing around with Excel spreadsheets, but unfortunately it doesn't quite work that way. So we'll give an example here. So this is very basic floor ceiling assembly, 2x10 wood joists. And this first one, we just have a single layer wood subfloor, plywood or OSB, and there's some bad insulation in the joist cavities. And then our second test has no subfloor. So the joist cavities are exposed at the top, but then we have a ceiling down below. And it's just a single layer of, I think, 5/8 gypsum board attached with resilient channels. So for the top, the subfloor alone, we have an STC 24. For the ceiling, we have an STC 27. So just add them together, we get a 51, and we meet code, right? Code minimum is STC 50, so we're good. Nope. Unfortunately, when you actually build this assembly and you go test it, what they got was an STC 49. Now, it's only a 2-point difference. It's a very small difference. But the reason I picked this rather than some other instance where there was maybe a bigger spread in the STC ratings between like just the addition versus the actual tested value is that this one illustrates why this sort of myth or misconception could get you into trouble. Because if you just add them, you think, oh, I've got an assembly that meets code. It's above the minimum of 51. But if you actually go test it, it doesn't. And now you're in trouble. So the next myth or misconception is that you can add a delta IIC to any assembly. And I haven't really defined a delta IIC in here. That's not the purpose of this to talk about it. But a delta IIC is just a measurement in the change of an IIC rating for a flooring and underlayment when they're applied. And it's specific in the test that they are tested always on a 6-inch concrete slab. So we've got a delta IIC for this flooring and underlayment combination. I think this was an engineered wood floor, loose laid on a 5mm recycled rubber QT underlayment. And so then we take an open web truss assembly. This is a very high performing open web truss assembly. It's got 1.5 inches of gypsum concrete on a 3/4 inch Acoustimat. We've got bad insulation in the cavity. We have the PAC RSIC-1 clips with 2 layers of gypsum board for the ceiling. So that assembly alone is an IIC 62, which is a really good rating. But if we add the two, add delta IIC of 24 to 62, do we get an IIC 86? I mean, that would be awesome. That's better than carpet. This is a phenomenal rating. Like, we're good. Let's go home. Unfortunately, it doesn't quite work out that way. So the assembly as a whole gets just an IIC 68. Now, an IIC 68, especially on an open web truss, is no mean feat. Like, that's a great rating, but it's definitely not an 86, right? There's a big gap between just adding the IIC and the delta IIC and what you get when you test the entire assembly. Another one that I've heard a lot is just people asking for the rating for an acoustical product itself. And when we're talking about isolation products like sound isolation clips or resilient underlayments, those kinds of things, they're parts of a system, right? And the system as a whole, that floor ceiling assembly or wall assembly, has these ratings, but the components themselves don't have those ratings. So just a very basic example, here's the same RSIC clip in a 2x4 wood stud wall, but depending on the layers of gypsum board that we have, we get two different ratings, an STC 56 with a single layer of gypsum board each side, and an STC 62 with 2 layers of gypsum board each side. And really sort of the analogy that I like to give for this is, you know, like if I put on Michael Jordan shoes, or the same kind of shoes that Michael Jordan wears, right? Like when he wears them, he's great at basketball. But when I put them on, I'm not great at basketball. I'm still terrible at basketball, right? Because it's not just the shoes, it's the whole system, right? It's the same thing for acoustical products. If you put a good acoustical product in a very poor assembly otherwise, you're still not going to necessarily get great acoustical results. All right, so now let's dig into the details a little bit more. So now we're going to talk about reading ISPL and TL graphs. So if you're an acoustical consultant and you're watching this, you're familiar with these things. You've probably spent a lot of time poring over them. If you're an architect or a contractor, maybe you've probably spent less time looking at these, but maybe you've seen them come through in test reports for acoustical products. So these graphs give us details of the assembly's performance beyond just the single number STC and IIC ratings. And why, as acousticians, we look at these a lot is because of those details. They tell us a lot more about what the assembly is doing and where the possible noise issues are. And that helps us determine what we might need to do to improve the performance of that assembly, to design better and quieter buildings. So we have two different things, right? So the ISPL is the impact sound pressure level. It's measured in decibels. That's the way that we measure sound levels. And it really tells us how loud are the impacts in the space below the assembly, right? And these are measured as part of an IIC test when we're using the tapping machine. TL, also measured in decibels, that's the transmission loss. And it tells us how much does the assembly reduce the noise levels from one side to the other. So we use this in STC tests, or also all of those field-related versions of sort of the STC, airborne sound transmission test. So if we look at this graph on the right, we're going to kind of break down the components of it and talk about it a little bit. So an important one is the frequency that's given in hertz. And you'll see the frequency down here on the horizontal axis or the x-axis. For frequencies, the low numbers equal low frequencies. So that's over here on the left-hand side of the axis, right? And I'm a musician, I'm an upright bass player, so I always like to use that as an example. So you think of an upright bass or a bass guitar, that's low frequency. And on the other side of that, the higher numbers are higher frequencies. And you can think of a violin for that. Maybe those of you who aren't so musically inclined, you can think about a diesel train, big diesel train, a lot of low frequency energy from that. On the other end is a fire alarm. And actually in sort of Googling this, trying to find images and things, I found that those fire alarms are often at this upper frequency range for this IIC range of 3,150 hertz. So that sort of gives you the idea of that frequency range. And you can think of each of these frequencies on this graph as kind of like keys on a piano, right? So you think about each key on the piano is a different note. They're also, each one is a different frequency. We can think about frequencies in terms of a pitch or a note, a musical note. And on this graph, you see the blue line with the dots on it, you see here. So that would be the sort of like actual measured levels. And each point on here represents the sound level at that particular frequency. So you can think about it as how hard you're hitting each one of these individual keys on the piano. And in the past, as I've shown this to people and I've tried to explain it to them, one of the questions I often get is, well, how do you have all of these different ones at the same time? Well, it's just like playing a bunch of keys on the piano or strings on a guitar at the same time. I mean, you could take both of your arms and just smash all of the keys on the piano. And that's kind of what we're doing, especially with impact sound, is we're just hitting all of the keys on the piano. So we're playing all of these different notes at the same time. And depending on how hard we hit each one of those keys, we get different sound levels at those different keys or those different frequencies. And bonus points to anybody watching this if you can identify the issue with this piano. All right, so now hopefully we understand a little bit more about the graph, what it is. So we've got frequency on the x-axis, the horizontal axis, and then on the vertical axis on the left-hand side, or the y-axis, for STC calculation, we have our transmission loss. That's how much we've reduced the noise from one side to the other. And on the IIC graph, we have the impact sound pressure level, which is how loud is it in the space down below. And so we have in gray our measured levels, so our measured transmission losses. That's how much reduction we got from one side to the other. And then in orange, we have this standard curve, right? And the way we get the overall STC rating is we do a curve fit. We just shift this curve up until we hit some thresholds. We hit these caps, and then that sets our STC rating. So for the STC, we're looking at the sound transmission loss from one side to the other. So the higher the transmission loss, the better, because we're reducing the sound more, right? So as we shift that curve up, anytime where the measured curve, in this instance, the gray, falls below the shifted curve, that's a deficiency, because we're not getting as much transmission loss as what's in the curve. So deficiency sort of has a negative connotation, but it's really just, is it below that curve or not? So you can see as we shift the curve up here in this animation, we get these little orange bars popping up at the top. Those are the deficiencies increasing as we go up. And for our STC rating, the total deficiencies, so you add up all of those orange bars, the total deficiencies can't be more than 32, and you can't have a deficiency of more than 8 at any one frequency. So you can see as we increase this, we keep going until the sum of deficiencies is above 32, and then we pop back down to 60, and that's our STC rating. The IIC rating works in much the same way, except that we're shifting the curve the opposite direction. We're going down instead of up. Because remember, for the IIC, we're measuring the impact sound pressure levels, or the ISPLs, and that's how loud it is down below. So the lower the number, the quieter it is, the better. So we shift the curve down, and that keeps getting higher or better IIC ratings. But we have the same sort of parameters. We can't have a total number of deficiencies more than 32, and we can't have a max deficiency more than 8. In this case, since higher means louder, anything that is above that orange curve is considered a deficiency. And so you can see as that orange curve goes down and that gray line gets further and further above the orange curve, the deficiencies down at the bottom go up. That's a lot to take in. You can come back and look at this. Hopefully this makes sense after you spend some time kind of looking at it and thinking about it. Another way that can be helpful to do this and think about this is actually a spectrogram. So a spectrogram is a really cool way of visualizing sound. It gives us even more information that's what's on those other graphs. If you thought that was information overload, well, let me introduce you to the spectrogram. So on a spectrogram here, we're showing frequency again in the horizontal axis. And so we go lower in frequency as we go left, and we go higher in frequency as we go right. And in this instance, we've got a piano keyboard up here again, sort of to show us the changes in frequencies, like different frequencies or like different notes. And but this piano is correctly laid out. So here we have two different things. So I think this was me tapping on my desk with like a pencil lead. And so there's more high frequency sound in this. And then I banged on my fist with, or I'm on my desk with my fist. And there's a lot more low frequency content. And so in this, we've got frequency in the x-axis, and there's actual time. So as you look at this in real time, you'll see it scroll through. And then level is the colors. So black is totally quiet, red is really loud, at least relatively speaking. And I got this from this website, amacoustics.com, and their analyzer. So if you go to this link here, you can get this and get your mic set up on your computer, and you can play around with this, and you can see it scroll through in real time. As you make different sounds, you can see the colors change on this. And it might take some time playing around with it before it sort of starts to sink in what it is and what's going on. But it's a really great tool, and I encourage you to go play with it. Look really silly, make a bunch of weird sounds, see what it does. Say different vowel sounds like A, E, I, O, U. See how that changes, whistle into it. I don't know, do all kinds of things, play around with it. I think if this stuff is new to you, it will help you better understand it. And if you're an acoustics nerd like me, you'll also have a ton of fun playing with this. So go check that out. It's a really cool site. They also have some other cool acoustic tools. Now that we've gotten through all of that, hopefully we've got a little bit better understanding of the STC and IIC ratings, how they're calculated, how they're measured, where they come from, what on earth those graphs are. Let's start talking about some of the shortcomings. And we'll use that other information to help explain the shortcomings. So STC, the rating itself and the AFCM standard date back to the 1960s, I think. And it was really designed around speech, which was one of the predominant noise sources that people were trying to address, especially in offices and multifamily housing situations back then. And I think in part because of that, the STC rating uses a limited frequency range. So this graph that we showed before, we go from a lower frequency of 125 hertz to an upper frequency, a high frequency of 4,000 hertz. And that's the frequency range that we use to calculate the STC rating. That's what we measure to get our transmission loss values and then calculate the STC. But here's the full range, at least theoretical range of what we can hear. If you've ever listened to loud music, or you've just, aged inevitably, that upper frequency range, you probably can't hear up to 20,000 hertz. But then we go way down to 20 hertz, right? And so there's this huge frequency range outside of what's being measured by the STC rating that we're not accounting for. And as you can see, the transmission loss values, so the level of noise reduction, goes up as we go up in frequency. So really the stuff up above 4,000 hertz, we probably don't need to worry about too much, because if we're good at 4,000 hertz, we're probably good above that as well. And typically we see these STC curves, they go up, the transmission loss increases as we go up in frequency. So as you go down in frequency, you go below 125 hertz, the transmission loss, or the noise reduction, decreases. So we get less noise reduction. That means more of the noise gets through the wall and we hear it on the other side. If we're just talking about speech, most of the speech energy, right, the sound that we hear from speech, occurs in that 125 hertz to 4,000 hertz range. But if we're talking about somebody's home theater system, the subwoofers live in that world below 125 hertz. So there's all of this sound that's being generated that we're not accounting for at all in our STC rating and our STC calculations. So the STC rating, the single number, doesn't really tell us the whole story. It doesn't tell us anything about what's going on below 125 hertz or above 4,000 hertz. But it also doesn't tell us about these sort of shifts, these dips and peaks in this curve. And depending on the noise source that we're looking at, those may be important. And the other really important point is going back to that quote, right? Code minimum does not guarantee satisfaction. I mean, one is just if you have an STC 50 wall, even for speech, you get kids yelling on the other side of it or something like that, or somebody that just plays their TV loud, and it's not, a big home theater system, but it's just the speech from the TV. That may still be annoying for somebody if it's just an STC 50 wall or floor ceiling assembly. But also if somebody's got a big subwoofer for their home theater system, STC rating and the code minimums aren't really addressing that at all because of this limited frequency range. All right, IIC. IIC has some similar ones, but it actually has more shortcomings, I would say, than the STC rating. So the IIC is designed around footsteps. And one of the issues with that is we have a lot of other impact sources besides footsteps that we need to deal with in buildings. And a big one of those is gyms and the whole health and wellness and fitness trend. And so we see more and more and bigger fitness facilities in hotels, apartment buildings, condos, all of these different spaces. And if you think back to the tapping machine that I talked about for the IIC test, right? It's these little about 1 pound weights that are dropped from maybe a couple inches onto the floor. That's the impact that we're using for an IIC test. But then you think about a gym scenario where you've got somebody lifting, a 50-pound dumbbell as they're sitting on the bench and then they drop it at the end of their reps. That's a completely different, much bigger, much heavier impact than the little 1 pound weights that are used in the IIC test. Or, in a big gym environment, you might have somebody that's, doing cleans where they're lifting a barbell over their head of, 100, 150, 200 pounds or something like that, and they're dropping that, or they're doing deadlifts of even more weight, right? So these really big impacts. And the IIC rating just really doesn't do anything to tell us about what happens when you hit the floor that hard. The IIC also has the limitation of a limited frequency range, just like the STC. The IIC frequency range is slightly shifted from the STC. It goes from 100 hertz to 3,150 hertz. But again, here's the range of what we can actually hear, from 20 hertz to 20,000 hertz. And with IIC, our impact sound pressure levels, so how loud it is in the space below, tends to go down with increasing frequency. But that's not always the case, and that's another shortcoming that we'll talk about in a second. But we tend to have some of the loudest impact sound pressure levels at low frequencies and below 100 hertz, which is the cutoff for the IIC range and calculation. So there's a lot of stuff going on below 100 hertz that might be really important, but we're not considering it at all when we calculate an IIC rating. So here again, a single number doesn't tell the whole story. It doesn't tell us about where these deficiencies are, where we've got low or quiet impact sound pressure levels and where we have high impact sound pressure levels. And there's a lot more variation in the shape of these impact sound pressure level, these curves for IICs, in that the shape of that gray line. And I'll show you that here in just a minute. And again, code minimum does not guarantee satisfaction, and that is even more the case for the IIC rating. And that's just for basic footsteps too. It's not just if you've got big heavyweights in a gym, it's just basic footsteps. And we'll give an example of that also. So that example is a paper by Blazier and Dupree that was written, published back in 1994. So there was a big class action lawsuit. So there was a large luxury condominium building in the San Francisco area, and an $80 million class action lawsuit was brought against the developers of that building. And one of the major claims in that was annoyance from excessive noise and vibration due to footsteps. Oftentimes when we think about impact sound control, carpet and pad is sort of the go-to, right? We think if we've got carpet and pad, we're good to go. We get such great IIC ratings with carpet and pad. That's not an issue, right? But in this case, the complaints that brought up this lawsuit were from areas without carpet, but also areas with carpet. And it's not like there were just a few from the carpeted areas and the bulk of them were for the areas with tile or engineered wood or hardwood or something like that. There were lots from the carpeted areas. And the complaints really revolved around thuds, thumps, and booming, which are these lower frequency sounds, right? Those were the biggest source of complaints. And I think this is a really powerful quote from that paper. This is, the IIC rating of a floor system is meaningless with respect to the perception of these low frequency components of footfall noise because the methodology ignores the frequency spectrum below 100 Hertz. So we've got all this stuff, these booms and thuds and everything happening below 100 Hertz, but we've completely ignored it in our IIC rating. Here we have a bunch of different IIC or ISPL curves. Each colored line here on this graph represents a different floor ceiling assembly that PAC has tested at a lab. So each curve represents all the measured ISPL levels for that particular floor ceiling assembly. And these are the curves that we would go through and we would do the IIC calculation that we went through previously and we would come up with an IIC rating. Now the crazy thing here is that for all of these that look entirely different, they have very different shapes, right? There's this huge range of them. Every single one of these, if you go through and you do the IIC calculation, you get the same rating. You get an IIC 55. And even if we, we're showing a frequency range that's wider than what we use for the IIC, but even if we just look at the IIC range of 100 Hertz to 3,150 Hertz, we see that there's still this massive variation in the measured ISPL or impact sound pressure levels for these different assemblies. So at some particular frequency on one assembly, it would be way louder in the downstairs receiving room than it would be for the other assembly. So let's look at that variation. Down at the low end at 100 Hertz, we have a minimum of 52 and a maximum of 65. So a 13 dB range between the quietest measurement and the loudest measurement at 100 Hertz. And again, keep in mind, these are all IIC 55 assemblies. And for reference, a 10 dB change in level is usually perceived as a doubling in loudness. So the loudest assembly down here at 100 Hertz would seem more than twice as loud as the quietest assembly. Now, let's go to the other end of the spectrum. Let's look at the highest frequency in the IIC range, 3,150 Hertz. Here we have an even broader spread between these. So we have a minimum of 5 dB, which just barely audible, extremely quiet, and a maximum of 45 dB. So a 40 dB spread between the quietest and the loudest. And this really shows that, all of these, again, it's the exact same IIC rating. They're all IIC 55. So if we're just looking at a single number, we're missing all of this movement that's going on and all of the differences in these assemblies. And it just goes to show how these single number ratings, especially the IIC rating, doesn't really tell us what's going on. And that's why we have these new standards, the HIIC and the LIIC, that we're going to talk about. And that brings us to the HIIC and the LIIC. So there was a lot of work that was put into the development of these, primarily by the folks at Vinaclausen and Associates. They've done a lot of research and reporting lots of papers, conference papers on this. And what they found is that in those graphs that I showed before, really you have this sort of low frequency range and this high frequency range, and they sort of tend to operate and move independently of each other. You can make changes to an assembly that improve the high frequency stuff, but do nothing for the low frequency stuff. Or you can make changes to an assembly that maybe improve the low frequency stuff, but don't necessarily change the high frequency stuff. Or you can have different assemblies that perform well in different areas, as we kind of saw from that graph before. So the HIIC stands for the High Frequency Impact Insulation class. So this all stems back to the IIC, the Impact Insulation class, right? The tapping machine, bang on the floor, see how loud it is down below. But this is just looking at the high frequency portion of that. The standard is ASTM E3222. And you can think about this section of it, the high frequency stuff, is the clicks and clacks from impacts. And it's the range from 400 hertz to 3150 hertz. And I've got the high heel here because you can think about sort of that sound of high heels on a hard surface floor. It could also be, hard surfaced dress shoes or something, men's dress shoes or anything else, or dog's nails on the floor, something like that, right? The LIIC stands for Low Frequency Impact Insulation Class. The ASTM standard is E3207. And this really looks at the thuds and the thumps that Blazier and Dupree determined were the issue as part of that class action lawsuit and the things that were unaccounted for by the IIC rating. And because Blazier and Dupree in part says, because we ignore the things below 100 hertz, the IIC rating is meaningless, especially for these thuds and thumps. The LIIC looks at that range below 100 hertz. So it looks at the range from 50 to 80 hertz. And you can think about this as somebody clomping around in some big heavy like work boots. The HIIC is easily measured as part of an IIC test because if you see here, the orange line, right, that's the range that we're measuring and using to calculate the IIC rating. And the HIIC range all falls within that. So if we've got a past IIC test that happened before the HIIC standard existed, we can still go back, take that measured data, and calculate an HIIC. Now, it won't necessarily be an official laboratory report, I guess, unless we have the lab go back and do it, but we can get good information about it. And I've done that for PAC based on a lot of our old tests, and you can find that in our online databases. The HIIC can be very useful for evaluating flooring and underlayments. Flooring and underlayments really make big differences in this HIIC range. And so you can use that to better differentiate between them and help make some sort of better design decisions maybe. Ceiling isolators can also have a big impact on this HIIC range. LIIC, this thumps and thuds low frequency range, is a totally different animal. So LIIC can't always be calculated from previous IIC data. A lot of times the lab reports stop at 100 hertz or maybe 80 hertz, and you don't have the 50, 63, and 80 hertz information that you need in order to calculate the LIIC. So in PAC's database of old test data, there's a number of tests where I can't go back and calculate a theoretical LIIC because I just don't have the data to do it. LIIC ratings are rarely affected by flooring and underlayment. There's certainly situations where that's not the case. If you're doing big built-up floating floor systems, they can definitely affect an LIIC rating. But generally, flooring and thin underlayments have minimal effects on the LIIC. But LIIC can be useful for evaluating ceiling isolation because you can get bigger changes in the LIIC rating from ceiling isolators. Now, there are some very important caveats to keep in mind with the LIIC rating in particular. Low frequencies are hard to measure, and I won't go into all the sort of physics basis for that. If you've got an acoustical consultant friend, you can ask them about that. But it's important to keep in mind that there's much lower accuracy and precision for LIIC ratings and really for lower frequency measurements like this. And yes, there is a difference between accuracy and precision. Also, there is an unknown and probably low correlation between labs. So for LIIC ratings. So if we go and we build an assembly and test it in one lab, and then we build that exact same assembly and test it in another lab, we're not necessarily going to get LIIC ratings that are very close. That's actually an issue that exists just for IIC ratings themselves, but it's even expounded for the LIIC ratings. I'd say that there's also fairly unknown and probably low correlation between lab and field tests for LIIC. Now, with IIC, there's also can be fairly low correlation between a lab test and a field test. In part, that's because of the flanking paths that are included in the field test and not in the lab test. It also could be because of construction defects in the field construction versus the lab construction. But all of those issues apply to the LIIC ratings, but there are other things also that complicate it and reduce that correlation between lab and field. So just because you've gotten this rating, LIIC rating in the lab doesn't mean you can necessarily go get it or something similar in the field. And so okay, well, what's the point? What's the use of the LIIC rating? One place where I think you can use it fairly safely is to compare assemblies tests done within the same lab, especially, at a similar time period and things like that. So again, within PAC's testing database, I have things where I'm starting to calculate LIIC ratings, and we'll start to present that. And we've done big test series where we've compared different ceiling isolators, and it's all the same lab test series. We're there for several days and we do a bunch of tests. So it's back to back to back tests. And we've controlled as many variables as possible so we can get as good of an apples to apples comparison as is possible. All right, last but not least, methods of improvement. Flooring and underlayments. So as I said before, flooring and underlayments can make big differences in your IIC ratings and your HIIC ratings, not so much your LIIC ratings. So here I have 2 example assemblies. Again, these were tested at the exact same lab. These are part of the same lab test series, so they were probably done on the same day or within a day of each other. It's an 18-inch open web truss. You can see all the details there. The big difference is the top one is just bare gypsum concrete, and on the bottom one, we've added engineered wood and a 2mm rubber underlayment. And you can see that the STC rating actually goes down a point. It's 1 point, pretty negligible. The IIC rating goes up 12 points. That's a big improvement, and it goes from well below code of 50 to well above code. The HIIC rating goes up even more. It goes from 41 to 63, so a 22-point improvement. Interestingly, the LIIC rating actually goes down a few points. And there is some sort of physics reasoning for why that could happen. And I think that, that is sort of a meaningful difference here. Like I gave all these caveats, right? So that is probably a noticeable change and probably a repeatable one for this kind of assembly. But really, flooring and underlayment, very minimal effect on STC, not a big effect necessarily on LIIC, but big effects on HIIC and IIC. Ceiling isolators. Here again, we have 2 test assemblies from the same lab. These are different test series, but they were still done within the same year, within a few months of each other, I think. And the only difference here is the top assembly is just a layer of Type C gypsum board attached with RC Deluxe. And on the bottom one, we've got the same Type C gypsum board and the RC Deluxe, but we've added PAC's RC1 boost isolator in the attachment between the RC channel and the bottom of the open web truss. And here we see STC, again, negligible change, only a point, but our IIC rating has gone up 5 points from a 55 to a 60, right? A really great rating. And our HIIC has also gone up 5 points from a 63 to a 68. But here, our LIIC has also gone up 6 points from a 48 to a 54. So we see we get a significant improvement in the LIIC from this ceiling isolator. Mass is another way that we can improve these. So here we've taken just a bare 6-inch concrete slab, and then we have a bare 10-inch concrete slab. So really the only thing we've changed is, the thickness of this and the mass, right? We've really increased the weight or the mass of this. So all of these parameters go up: the STC, the IIC, the HIIC, and the LIIC. And the other thing that's important to note about this is, for these bare concrete slabs, look at the IIC rating. Keep in mind that code minimum is 50, and even that isn't sufficient to eliminate annoyance and complaints and potential health effects from neighbor noise and all of that. And here for a bare concrete slab, we're at IIC 29, IIC 30. Those are very low, very not good ratings. And the HIICs are also low, but the LIICs are really high, much higher than the open web truss ones that had pretty good IIC and HIIC ratings. And this is really the difference between those two sort of frequency domains for impact sound, that high frequency HIIC component and the low frequency LIIC component. Insulation is another way that you can improve it. So the top assembly has no insulation in the cavity. The bottom assembly has 3.5 inches of bad insulation in the cavity. And adding insulation improves the STC, the IIC, the HIIC, and the LIIC. So adding bad insulation, or maybe increasing the amount of bad insulation in an assembly, can be a good way to improve your acoustical ratings. But with all of this stuff, and insulation is a great example, you have to keep in mind your fire ratings. A lot of times, like with this open web truss, you can't increase the thickness of the bad insulation beyond the 3.5 inches shown here without having to make other changes to your assembly to maintain a 1-hour fire rating. And that may be adding an additional layer of gypsum board, or it may be reducing the channel of the spacing of the resilient channel, which could affect your acoustical performance. Stiffness and damping are also ways that you can change the acoustical performance of an assembly. Beyond the scope of this, what I'm going to get into, if you're curious about these, find an acoustical consultant, call them up and ask them about it. In conclusion, the basic code requirements are STC and IIC 50, but as we've talked about, there's a lot of limitations to those ratings, and just meeting the basic code minimums will not guarantee, a satisfied customer. Because the STC and IIC have significant limitations, the IIC especially. IIC limitations really are significant, and that is the reason for the new HIIC and LIIC standards, which really can be good design tools to help improve the acoustical performance of the buildings that we're all working on. Ceiling isolation is a good way to get better HIIC and LIIC performance. Again, the code requirements are minimums, and the minimum is important. And I'll just leave you with this quote again. Thank you for joining us for this. Thank you for watching. Our next presentation will be, usually we do these on the 4th Thursday of every month, but in November that would be Thanksgiving. So we're going to do it on the 3rd Thursday. You can go to the tiny URL link right there to register. The next one is going to be on how PAC can help address product cost and availability issues. We're going to talk about reducing gypsum board, reducing framing, issues with resilient channel availability, and a bunch of other things, because right now more than ever, product availability and product cost increases are a really big deal in the building and construction industry and just everywhere, right? Consumer products, all kinds of stuff. One more quick plug before I wrap this up. I'd like to encourage everybody here to go check out our online assembly selectors. We have one for walls and one for floor ceiling assemblies. You can filter by a whole bunch of different parameters to try and filter down and find the assembly that provides the acoustical performance and also the fire performance that you need for your project. You can go to the link at the top there to register. You do have to give us a name and phone number and that good stuff in order to register for access. But then you've got 24/7 access to this, and it's a really great tool, and I think there's a lot of helpful information there. And with that, thank you again for watching. We've got a bunch of contact info here, and another important thing for any architects watching this, we do have an online course through AEC Daily where you can go get CEU credits for AIA, and they count as HSW credits. Watching this doesn't get you AIA credits, but you can go do that. It's an online self-directed course, and AEC will report to AIA for you so you can get those credits taken care of. Thanks for watching, and take care.